Imagine standing outside at noon. Within seconds, an invisible flood of energy crashes into your body. Not enough to knock you over, but enough to power hundreds of light bulbs if you could capture it. Now imagine that same invisible rain falling across every desert, rooftop, parking lot, and empty field on Earth. It raises an irresistible question. If the sun gives us so much energy for free, why are we still burning coal, oil, and gas? The answer turns out to be far more fascinating than simply solar panels aren't good enough. It begins inside one of the most ordinary-looking materials on the planet, silicon. To most people, it's just sand. But when purified and carefully arranged into crystals, silicon becomes something extraordinary. It can transform sunlight into electricity without spinning a turbine, burning fuel, or making any noise at all. No flames, no moving gears, no smoke. Just light becoming power. That almost sounds like magic, except it's physics. Deep inside every solar cell, billions of atoms are lined up in a perfectly ordered crystal. Each atom shares its electrons with neighboring atoms so tightly that almost nothing moves. Left alone, this crystal behaves like a city where every resident stays inside their home forever. No traffic, no current, no electricity. So engineers perform a clever trick. They deliberately add tiny amounts of different elements into separate layers of silicon. One side ends up with extra electrons looking for somewhere to go. The other develops tiny vacancies where electrons would happily fit. When these two layers touch, something remarkable happens. Nature immediately tries to restore balance. Some electrons drift across the boundary, creating an invisible electric field, like a microscopic one-way street hidden inside the material. Nothing is moving yet, but the trap has been set. Now enter the sun. Sunlight isn't just warmth.
It's made of tiny packets of energy called photons, each racing through space after an 8-minute journey from the solar surface. Most continue harmlessly onward, but every so often, one photon strikes the silicon with exactly the right amount of energy. It's enough to knock an electron free. For the first time, that electron can move. And thanks to the electric field waiting inside the cell, it knows exactly which direction to travel. Instead of wandering randomly, it's pushed toward one side of the panel. Metal contacts collect these travelers, guiding them into wires outside the panel. Only then do they perform useful work. Lighting a room, charging a phone, running a refrigerator, powering a hospital. After completing the journey, the electrons simply return to where they started, ready to repeat the entire cycle millions of times every second. Nothing inside the panel wears out from this motion. Unlike an engine, almost nothing is rubbing, grinding, or colliding. That explains one of solar energy's biggest advantages. A quality solar panel can quietly generate electricity for decades. But if the process is so elegant, why hasn't it already taken over the world? The first obstacle isn't technology, it's geography. The sun doesn't treat every place equally. Near the equator, sunlight arrives almost directly overhead. Closer to the poles, it spreads over larger areas and spends much of the year hidden behind long winters or low horizons. Some cities enjoy endless sunshine.
Others spend weeks beneath clouds. Then comes the obvious problem: night. Every solar panel on Earth experiences the same daily interruption. No sunlight means no new electricity. Civilization, however, refuses to pause. Hospitals don't close after sunset. Factories don't wait until morning. Data centers don't sleep. That means solar energy must solve a challenge far bigger than simply generating electricity. It must store it. Today's batteries have improved dramatically, but storing enormous amounts of electricity remains expensive and resource-intensive. Engineers are exploring alternatives, from pumping water uphill during sunny hours to storing energy as hydrogen or even inside massive underground systems. Generating electricity is only half the puzzle. Saving it for later is equally important. Even under perfect sunlight, another limitation appears. No solar panel captures every photon. Some light reflects away before entering the material. Some photons don't carry enough energy.
Others carry too much, wasting the excess as heat. And sometimes, newly freed electrons reunite with their missing partners before escaping the cell, canceling the entire process. Every one of these tiny losses reduces efficiency. Modern commercial panels usually convert only a fraction of incoming sunlight into usable electricity. That may sound disappointing, until you realize how much sunlight actually reaches Earth. Every hour, the sun delivers more energy to our planet than humanity uses in an entire year. Suddenly, even modest efficiency begins to look impressive. The real question isn't whether enough energy exists. It's whether we can collect, transport, and manage it. That requires space, lots of it. At first glance, covering vast areas with solar panels sounds impossible. But compare that land to the enormous deserts, industrial rooftops, highways, reservoirs, and parking lots already exposed to sunlight every day. Entire floating solar farms now cover reservoirs, reducing evaporation while producing electricity. Buildings are becoming power plants. Car parks are becoming miniature energy stations. Even transparent solar windows are beginning to blur the line between architecture and power generation. The future may not depend on one giant solar farm, it may depend on millions of smaller ones. Yet technology alone cannot decide the outcome. Energy systems evolve slowly because societies invest trillions of dollars in existing infrastructure. Power plants, transmission lines, fuel supply chains, and political interests don't disappear overnight. Replacing them requires decades of planning, investment, and cooperation. But history has shown that energy transitions do happen. Humanity once relied on wood, then coal, then oil and natural gas. Each transition reshaped civilization. Solar could become the next chapter, not because it's fashionable, but because it keeps becoming cheaper while improving year after year. Perhaps the most surprising impact isn't happening in wealthy nations. It's happening where electricity barely exists. Across many remote communities, extending traditional power lines can cost far more than installing local solar systems. For families who once depended on smoky kerosene lamps, a single rooftop panel can mean brighter evenings, cleaner air, refrigeration for medicine, internet access, and opportunities that simply weren't possible before. In these places, solar energy isn't replacing an old system. It's creating the first reliable one. That shift may ultimately prove more transformative than powering skyscrapers. So, will the entire world someday run entirely on sunlight? Maybe. Maybe not. The future will almost certainly include many energy sources working together. But one fact is difficult to ignore. Every sunrise delivers an energy supply beyond anything humanity has ever built. For billions of years, it has arrived on schedule without invoices, fuel deliveries, or maintenance crews. But every year, we learn how to capture a little more of that endless gift. And with every improvement, the idea that once sounded impossible begins to look a little more like tomorrow.